Hi everyone, in this video we are going to discuss this problem called divide nodes into the maximum number of groups. So the problem says that we will be given with an undirected graph with n number of nodes numbering from 1 to n, and we have to divide the graph in some number of groups such that two conditions follow. First condition is that each node should belong to one group, and the second property or second condition is that all the adjacent nodes should be present in adjacent groups. So let's take an example and try to understand the problem. Let's say we are given with this graph 1, 2, 3, 4, 5 and 6, right? So let's say this is the graph which is given to us. So now each node should belong to one group and all the adjacent nodes should be present in adjacent groups. So let's say we put 1 in G1, group 1. If we put 1 in group 1, then the adjacent of this should be present in the adjacent group. So the adjacent of 1 is 2, so 2 should be present in the adjacent group. So we can put 2 in group 2, okay? Now all the adjacents of 2 should be present in the adjacent group to G2. So 3 and 5 should be present in G3, 3 and 5, right? Similarly, all the adjacents of 3 and 5 should be present in a adjacent group to G3, right? So G4 is an adjacent group, G2 is also adjacent group. So we can put 6 and 4 in G4. Also we can put in G2, but we'll see why we are putting in G4, okay? So this is how we can divide this graph in some number of groups, right? So the question further says that if we are able to divide our graph in some number of groups following the two conditions, in that case we need to return the maximum number of groups in which we can divide our graph. So in this case we are able to divide our graph in 4 groups. So in that case the 4 will be our answer, right? And if we are not able to divide our graph following the given two condition, in that case we need to return -1, right? Okay, so this is the problem statement. Now we can try to think of a approach for this problem, okay? So see, one thing is clear that if we have a tree, in that case we will be able to divide our nodes in some number of groups for sure, right? Like if we do not have this cycle, then we can consider any BFS, right? So if we have this tree, so we can just say that 1 will be connected to 2, then 2 will be connected to 3 and 5, and 5 will be connected to 6 and 4, right? So if we are given with a tree, then we can consider any BFS, and that will follow both the conditions, right? In that case, we can just find out the maximum number of groups, right? So if we are given with a tree, then for sure our answer exists, right? So now let us see what difference it will make when we have cycles, okay? So we had a cycle here, right? We had a cycle here, but we were still able to divide our graph, right? In such a way that both the conditions follow. But will we be able to do the same thing if 2 is connected to 6? Will we be able to do the same thing? You can pause the video and think about it, right? So the answer is that we will not be able to divide this graph in such a way that both the conditions follow. Now let us see why, right? Okay, so like 1 is connected to 2, 2 is connected to 3, and 2 is connected to 5, right? Then 3 is connected to 6, 3 is also connected with 4, right? Okay. Now this was the case when we didn't have this edge, right? But now we have this edge, 2 to 6, okay? So this is violating the second property because 2 and 6 are adjacent, so they should be present in adjacent groups, but 2 and 6 are not in the adjacent groups. Now you can try to find out different ways or combinations for putting these nodes in these groups, but you will not find any way or combination which will follow both the properties. And the reason for that is this cycle, or you can say this cycle. So let us see why. So let us consider 2, 5 and 6. These three nodes are creating a cycle, okay? Now if we put 2 in any group, let's say we are putting in some group Gi, we are putting 2 in some group Gi. Now if we want to follow the second property, then we will have to put 5 either in Gi-1 or in Gi+1, right? Because 5 is the adjacent node, so they should be present in adjacent groups. So let's say we put 5 here in I+1 group. Now 6 is adjacent to 2, right? So 2 should either 6 should be present here or 6 should be present here. If we put 6 here, then 5 and 6 is violating the second property because they both are adjacent nodes and they are present in same group. They should be present in the different groups, okay? So we can't place 6 here if we have placed 5 here, okay? So the remaining option is that we can place 6 here. so that 2 follows second property with both the nodes. But still 5 and 6 are violating the second property, because 5 and 6 are adjacent nodes and they are not present in the adjacent groups, right? So if we have a cycle of length 3, in that case we will not be able to divide our graph such that the division follows both the properties, right? So like a cycle of length 4 was able to follow both the properties, but a cycle with length 3 is not able to follow the properties, right? So now let us take a cycle with length 5. So let's say we are given with 2, then 3, 4, 5 and 6. Let's say this is the cycle with length 5. So let's try to divide this in such a way that both the conditions follow. So if we put 2 in some group, then we can put 3 and 4 in the adjacent group. Now the problem is that 3 is adjacent to 6, so 6 should be either present here or should be present here. So if we put 6 here, then we can't put 5 here, right? We can't put 5 here. If we put 5 here, then 5 and 6 are adjacent, so they should be present in the adjacent groups, so they will not be able to follow the second property. So the problem is that So the problem with the odd length is that at the end we are left with 2 nodes which are adjacent to each other, right? And they are also adjacent to 2 nodes which are present in single group, right? So this will violate the second property in any combination, okay? And in even length, it's let's say we have length 6. So in that case we can put first element here, then second and third here, let's say, then fourth and fifth we can put here, and then sixth we can put here, right? So we are able to follow the second property because at the end we are left with only single node, right? Because if they are connected, so they are not adjacent, so they can be put in single group. They are not adjacent, so they can be put in single group, and we are left with only one node in at the end, or we can say at the edges, right? So that's why we are able to follow the second property. And even and in the case of odd length, we are left with 2 nodes, so we will not be able to follow the second property. Okay, so one thing is clear, that if we have cycles of odd length, then the answer will be -1, right? And if we do not have cycles with odd length, in that case we need to find out the maximum number of groups that we can generate. Okay, so now let us focus on this part. Now we know that if we have cycles of odd length, then we will not be able to divide our graph. But in other cases we will be able to divide our graph, right? So if we will be able to divide our graph, then now let us see how we can find out the maximum number of groups. So let us take an example. So let's take our previous example only, 1, 2, 3, 4, 5 and 6, 7. Okay, so let's say that we are given with this graph. Now there can be multiple ways in which we can divide this graph. For example, let's say let's have groups G1, G2, G3, G4 and G5, right? So if we start from, let's say, 5, then we can place 5. Now all the adjacents of 5 should come in this group, 3 and 4, right? Now all the adjacents of 3 and 4 should come in this group. So adjacent of 3 is 2 and 4 is also 2. And for 3 we have 6 also, right, which is our adjacent, so we can have 6 here also. Okay, now for 2 and 6, for 2 3 is already there, 4 is already there, 1 should be placed here. For 6 3 is already here, so for 6 7 should be placed here, right? So this is one way in which we can divide this graph. Now if we, let's say, start from 1, in that case the adjacent of 1 is 2, so 2 should come here. Now for 2 3 and 4 should come, 4 and 3 should come here. Now for 4, 5 should come here, and for 3 also 5 should come here. For 3, 6 should also come here, and for 6, 7 should come here. Okay. So in this way we got, we were able to divide our graph in 4 groups, and in this way we were able to divide our graph in 5 ways, right? And can we say that these ways are nothing but a BFS traversal of this graph starting from a particular node, right? So if we start our BFS traversal of this graph from 5, then we got 4 levels, and here we got 5 levels, right? So these ways are nothing but BFS traversals of this particular graph. And because we want to maximize the number of groups, then can we say that we will be interested in a BFS traversal which is having the maximum number of levels, right? And what can be the maximum number of levels in a BFS traversal? Can we say it will at max be the maximum distance between any 2 nodes? For example, what is the farthest node for this 3? So can we say that for this 3, if we go 1 right, then 2, so this is the third node, right? So, and here also 1 is the third node, and for 3 this is also the third node. So we can say that the farthest node from 3 is at distance 3. For 2, the farthest node is this 7, and this is 4 distance away, if we are considering number of nodes equals to the number of equals to the distance. So in that case 7 is the farthest, and the distance between 2 and 7 is 4. Okay. Now for 5, what is the farthest node? For 5, the farthest node is 1, 2, 3, 4. 1, 2, 3, 4. So the 4 is the maximum distance, right? For 4, 1, 2, 3, 4, 5. So 5 is the farthest node, right? For 6, 1, 2, 3, 1, 2, 3, 4. 1, 2, 3, 4, right? So 4 is the maximum farthest node. For 7, what is the farthest node? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, right? So 5 is the farthest node, and for 1 also 7 is the farthest node, which is at a distance of 5, right? So if we have this information, for every node we know what is the farthest node, shortest distance between this node and the farthest node, right? If we have this information, then we can find out what can be the maximum number of levels that we can have, or maximum number of groups that we can have, because for this node 5 is the shortest distance between this node and the farthest node, right? So 5 nodes have distance 5. So starting from 4, 1 and 7, we will be able to have 5 levels in our BFS. So we can say that 5 will be our answer in this case. Okay. So now we can say that if we have this information, then we can just take the maximum value out of these all values. So we can say in this case the maximum value is 5. So 5 will be the maximum number of groups, right? Okay. So this will be the case for this graph. Now the question says that graph can be disconnected. So for this component we know that this will be the answer. Now let us take one more component. Let's say we have 8 and 9. Okay, so for this component we can surely say that at max we can have 2 groups. Okay, so for this component we can have 5 groups, and for this component we can have 2 groups. Now we want to maximize the number of groups. In that, can we say that we can have a group G6 in which we can place 8 or 9, and we can have group 7 in which we can place 9, right? Because they should be connected, because they are connected and they should be present in adjacent groups, right? And why we are placing these 2 nodes here? Because we want to maximize the number of groups. So can we say that our final answer, if we have multiple components, in that case the final answer will be the maximum of this component, then maximum of this component, and the sum of this thing, 5 then plus 2. Okay, so if we have multiple components, let's say we have C1, C2, C3 and so on, right? Let's say we have 3 components only, and let's say the maximum value or maximum number of groups in which we can divide component 1 is M1, and maximum number of groups in which we can divide this component is M2, and maximum number of groups in which we can divide this component M3 is C3 is M3, right? So the final answer will be M1 plus M2 plus M3. Okay, this will be the case. So now let us try to code this whole thing. So let me just write the pseudo code first. So first we discussed that we will have to find out if we have odd length or not, right? So first we need to check for odd length cycles. Then this is the first thing which we need to do. And second thing which we need to do is we need to find out these values for every node. And what is these values? These values are the shortest distance from this node to the farthest node, right? We need to calculate this distance. So we need to find out the minimum distance between ith node to the farthest node for all the values for all the nodes. Okay, once we have this data, then for every connected component we need to find out the maximum, right? So then we need to, for every connected component, we need to find out the maximum value of this distance. We need to find maximum value. Okay, and then we just have to add all those values, and that will be our final answer, right? This is what we have discussed so far. So we'll write the pseudocode for this. Okay, so the first thing which we want to do is we want to find out if we have cycles with odd length or not, right? And for that, what we can use is we can use a concept of bipartite graph. So we'll not go into the depth, but we can just see the overview of that. So in bipartite graph, what we try to do is, let's say we are given with some graph. Let's say we have this 1, 2, 3, and 4, right? Now we have the cycle of 4. So in bipartite graph, we try to paint every node with the 2 of the colors. Like we will be given with 2 colors, red or blue, or something else, right? Then we have to paint every node with one of these 2 colors in such a way that no 2 adjacent nodes have the same color. For example, if we just paint this with red, then we can paint these 2 with blue only, because no 2 adjacents should have same color. And if you have painted these 2 nodes with blue, then this can only be painted with red, right? Similarly, if we have a cycle with odd length, let's say we have 1, 2, 3, 4, and 5, right? Now if we try to paint this node with the color red, then these 2 should be painted with color blue. Now these two nodes are painted with blue, so this will be painted with red, this will be painted with red, right? Now these 2 violate this property. Now these 2 violate the property because no 2 adjacent should have the same color, but they are having, right? So all the cycles with odd length will violate this property, and only the cycles with even length will pass, or no cycles will pass, right? So we can use this concept to find out if we have odd length or not, right? So I'll just write the pseudocode so that you guys can try coding it yourself, and you can find the whole solution in the description. So let's say the first thing which we will do is that we will have a if check is valid. So what we'll do, we'll first create the adjacency list, and then we can pass that adjacency list in this function. And let us just assume that this function will return us true or false. It will return true if we do not have any cycles with odd length, otherwise it will return false. So if this condition is false, is valid, this condition is false, that means we have cycles with odd length. In that case, we need to return -1. And this can be like this logic can be implemented in order of n using BFS, right? That will not be difficult. Okay. Now, once we have this clear with this step, then the second step is to find out the minimum distance between ith node and the farthest node from that ith node, right? So for that, what we can use is, for every node we can run a BFS. Like from first we can run a BFS, then from 2 we can run a BFS, and we can find out the like minimum distance between that node and the farthest node. So now let's have a vector in which we will store the distances. So it should have a size of n+1, and let's say like we do not need to initialize it to anything. Now what we can do is we can run a loop starting from 1 and till n, and what we can do is for every node we can call a BFS function. So we can call a BFS function which will return us the maximum distance, or we can say the minimum distance between that node and the farthest node. So adjacency list we will pass, and we will pass let's say the ith node for which we want to find out the distance. So it will return us that distance, and we will store it in this vector, right? Okay. Now the second like step is also done. Now we have to, like for every connected component, we need to find out the maximum value of this thing. Okay. So for that, what we can do is, let's say we have a visited array or vector visited n+1. Initially everything will be 0. Okay. Now for every node we can call a DFS, and whatever will be connected we can cover that part, and we can update it in visited array, and then we can keep on like traversing all the components. So we can start from 0, like from 1, and we can go till n. So if our current node is not visited, like initial value is 0, so if our visited of I is still 0, in that case we can say that ith node is not visited yet, right? That means this was not a part of any component which we have already visited. So now what we'll do, we'll call this DFS function, and this will traverse this entire component which is connected to ith node. So we can pass this visited as well, and this distance vector also, right? Now we can we are assuming that this DFS function will traverse the entire component, and it will mark every node as visited, and it will also return us the maximum value of that component. So let's say it will return us the maximum value, so we will store it somewhere. So let's say we have a variable starting initialized with 0. So whatever it will return, we will just add that to MA, this variable plus equals to, right? Okay, so because this DFS function will be called only once for a component, right? Because ith node is not visited, so we will call this function. It will visit all the nodes connected to this ith node and it will return us the maximum. Then it will not run for any node which was connected to I. Okay, so this DFS function will run only once for every connected component. So after this we can simply return MA. Okay, so this was pseudocode, and you can find out the entire solution in the description. So that's all for this video, and I'll see you in the next one.